Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 4.1.2, which is factoring with area models. And so we're going to be examining the model shown at the right. And it says, review what you learned in Chapter 4.1.1 by writing the area of the rectangle as the sum and as a product. So as a sum, if I'm going to write this area as a sum here, area as a sum, I'll just add up all the four inner pieces here. So that's going to be 10x squared minus 4x minus 35x plus 14. If I combine like terms, that's going to be 10x squared minus 39x plus 14. And that's my area as a sum. Again, that's the summation of all 4 points here, of all 4 miniature squares. The area as a product, well, that's going to require finding the dimensions of each side. So again, how did we do this in the last section? Well, what we did was we figured out how to divvy up the 10x squared first. Now, again, look at the adjacent boxes. The top box is negative 35, and the bottom right box here is negative 4x. Now, the 10 can be divided in a couple of ways. I can make it a 10 and a 1, or a 5 and a 2. If I decide to go 10x and 1x, there's nothing wrong with that, I guess, because I'll end up getting the lower left box correct. But look at the adjacent boxes. I have to multiply 10x by something down here now to get negative 4x. That's not going to be particularly easy or even possible. The 1 and the 35 won't be that bad either, but I feel like that's not going to be the right combination. Likewise, if I put the 5x here and the 2x here, again, the 35 really doesn't go well into this 2 here, and neither does the negative 4 into the 5. So I think my best option is to throw in a 5 right here and a 2 right here, because now the 2 can definitely multiply by a negative 2 to become negative 4x, and this 5 can multiply by a negative 7 in order to get this negative 35. And it just so happens that when I multiply negative 7 and negative 2, I get positive 14. And that coincidence is actually not a coincidence at all. Those puzzle pieces will fit together very, very nicely. So when I write the area as a product, I'm going to get 2x minus 7 times 5x minus 2, or the length or the height times the base. And so that's part A right here. We're writing the area as a sum and area as a product. And by the way, those two things are going to be equal pieces. They're going to be the same. And so now it says, does this area model fit Casey's pattern for diagonals? Now, we didn't talk about this in the last section, but Casey's pattern for the diagonals basically says that the diagonals of the boxes, so in other words, these two guys right there, right? If I multiply these purple boxes together, it will be the same result as if I multiply the orange rectangle. So if I do 10x squared times 14, I get 140x squared. And if I multiply the purple, well, 35 times 2 is already 70, but if I double that again, right, negative 35x times negative 4x, that's going to be 140 again, and notice how I get x squared, and the negative times negative is positive. So Casey's diagonal pattern does still work for this. All right, let's take a look at the next problem here. I'll be right back. In 4-13, the culmination of what we are doing will slowly start to come to pass here, where they tell us about factoring a quadratic expression, and they talk about a polynomial in the form ax squared plus bx plus c, with a not being 0. It's called a quadratic expression in standard form. And we're developing this method for factoring the quadratic without using algebra tiles, but in order to get there without using algebra tiles, they want us to first use algebra tiles. And so with A, they want us to factor 2x squared plus 5x plus 3. And we're going to go ahead and do that, except I've already done it. So part A looks like this. So at this point, you're supposed to get x, 1, 1, 1, and x and 1. And ultimately, this culminates into 2x plus 3. And x plus 1. And so now from here, what we're going to do is we're going to write this area as a product here. So that's going to be 2x plus 3 times x plus 1. And ultimately, that does, in fact, equal 2x squared plus 5x plus 3. Now, again, just because we have the quadratic in front of us, I do want to make sure that we're aware of all the pieces here. When they talk about this ax squared plus bx plus c, that's the general form of a quadratic. Similar to how you guys learned y equals mx plus b as the general form of a line, the ax squared plus bx plus c, the a in this case would be 2, b would be 5, and c would be 3. Get used to that expression. We're going to be talking about quadratics a lot over the next couple of chapters, and definitely it comes up a lot in future math classes. So this idea of the quadratic is definitely not something to be glossed over. So with A down, it says, when you factor using tiles, you need to determine how to arrange the tiles from a rectangle. Using the area model requires a slightly different process, and basically what they're trying to get us to do is they're trying to say, okay, without doing any area model tiles or algebra tiles, how can we build these on paper and not necessarily draw things up to scale? And that's fine. There's nothing wrong with that. We want to make sure that our drawings are compact. It says Miguel wants to use an area model to factor 3x squared plus 10x plus 8. And he knows that 3x and 8 go into the rectangle along the diagonals shown at the right. And then we got to finish the rectangle by deciding how to split the remaining term. Then we got to write the areas of product. So we got Miguel's rectangle right here. Now, if we look at the diagonals of this rectangle here, the 3x squared and the 8, we know they multiply to 24x squared. So what I want to do is I want to get two numbers in here that are going to multiply to become 24. And in this case, I think I'm going to go with 6 and 4. And so with here, I'm going to go and throw down a 6x and a 4x here. And now we're back into that whole notion of how do I get the dimensions. Now again, how did I know to choose 6 and 4? Well, 3 and 8 were already chosen by this guy. Okay, and so again, I'm looking for the same numbers that are going to multiply to 24x. And so how do I get this diagonal to multiply to 24x squared? Well, I just used 4 and 6, and it's a guess, and I could be wrong, but I don't think I am. And so we're just using Haley's, or Casey's diagonal pattern here, where the diagonals always end up having to multiply into the same thing. So here we go. I'm going to go and throw down my 3x here and my x right here. And I believe there's going to be a 4 right there and a 2 right there. And hopefully, again, that's making enough sense, right? I wanted to put the 3 here because I wanted to line up with the 6. The x can line up with the 4. No big deal. And so my area as a product is going to be 3x plus 4 times x plus 2. And there we have it. There goes B. It says, on C, Kelly wants a method to determine the factorization of 2x squared plus 7x plus 6, and she remembers Casey's pattern for the diagonals. Here we go again with Casey, right? She places the 2x and the 6 in the diagonals of the rectangle, and without factoring yet, do you know the two missing parts of the area model? So again, if I multiply the two diagonals together, I get 12x squared. Now, if I was a betting person, I would think that because 6 and 2 were already taken to multiply to 12, I would venture to guess, I'm going to go darken the color here, I would venture to guess that a 3x and a 4x go into these spots here. And that's because 3x times 4x would be 12x squared again. So how do I know what's going to go where? Let me go and just redraw this area model down here because it's running out of space with all the diagrams. And so, whoops, ugly. And so from here, I've got the 2x squared here and the 6. If I throw out a 3x and a 4x here, well, again, I'm going to go and throw the 2x and x in those places. I hope, again, that's obvious with the 2x lining up with the 4x. This would have to be a 2. This would have to be a 3. And now I've got my area as a product. So 2x plus 3 times x plus 2. Just to make sure, though, because, I keep throwing down these random numbers, and I haven't shown you how they actually work quite yet. And so from here, if I was to remultiply this thing, I could say this is going to be 2x squared, this could be 4x, this could be 3x, and this could be 6. Notice the pieces that I've just multiplied out here also correspond to pieces in the area model. And we know that if I sum up all these pieces in the area model, I get back to where I am here. But let's see if this is true all three ways. 2x squared plus 7x plus 6, I believe I'm back to where I started, so here we go. In 3 different ways, we showed how to factor an area as a product, an area as a sum into an area as a product. I will be back with the next section. In the last problem here, 4-14, it says factoring with an area model is especially convenient when algebra tiles are not available or when the number of necessary tiles becomes too large to manage. It says using a diamond problem helps avoid guessing and checking, which can be sometimes challenging. Using the process from problem 4-13, factor the 4x squared plus 17x plus 12. Now, I did mention we would see the return of an old friend, and that old friend is our good old buddy, the diamond problem. And so what I'm going to do is I'm going to slap down the area model first. And so the area model says that we are going to throw down, and I like to actually put down the 6x squared down here and the 12 up here. Now, if I use Casey's pattern of the diagonals, if I do 6x squared times 12, I'm going to get 72x squared. Now, again, that means that these two boxes need to, on the top left and the bottom right, need to also multiply to 72x squared. So I know that my product here is going to be 72x squared. Now, my sum is going to be the inside piece here, so that's going to be 17x. Now, where the diamond actually comes in handy is when I say, I'm looking for two numbers on the side now, and now we're back to something we recognize, that are going to multiply to 72x squared and add up to 17x. And what is that going to be? Well, that's going to be a 9x and an 8x, right? Because 9 plus 8 is 17. 9 times 8 is also 72. It will not matter where you put the 9x and the 8x. So I'm going to opt to put the 9x up top and the 8x on the side. And again, it won't matter. All that's going to impact where you put these is where the dimensions end up going. So because I have opted to put the 9x up top, it makes sense that I would not put the 3x right here for the 6x squared. It makes sense that if I was to break apart 6x into 2x and 3x, that 2x would go on the side because it links up with the 8x, and the 3x goes on bottom, linking up with the 9x. And then from here, what I end up getting is I end up getting a 3, because 3 times 3 is 9, and I get a 4 because 2 times 4 is 8. And so here I just add them up, and I have 3x plus 4 times 2x plus 3. Now, this is factoring. There are a lot of different ways to do it. There's actually another video that talks about the best method for factoring, and I'm the one who made it. And really, there's not one best method in my opinion. It really kind of boils down to what works for you. But I encourage you to check it out if you want to, or if you're working with someone else, and they show you a different method. Be open to different methods of doing things. And so from here, this is how the diamond problem really comes to fruition, along with the area models we've been doing. It all comes down to this notion of factoring quadratic expressions, which is what we're going to be doing a lot of in this next chapter. So I hope you found this video helpful. As always, please feel free to leave questions or comments in the comments area, and I will see you in the next episode.